Okay, so the next topic we will discuss is Zeeman effect. As we just understood and learned about the Stark effect. So Zeeman effect is similar, which was historically first discovered, and it is about an electron in an atom which is subjected to an external magnetic field. So what happens when you do that? What is the Hamiltonian? As we know that if there is a magnetic field, the Hamiltonian, the momentum picks up a EA, or I put the suffix external to make sure you clarify that it's an external field. PEA, the effective momentum becomes this. You have the usual Coulomb term, plus you have a B dot S term where the spin couples with the external magnetic moment, which comes from the external magnetic field couples with the spin magnetic moment, which is written as the form of B external dot S. And you have the usual other relativistic terms. Here I write down the LS coupling term, which has the zeta R prefactor, which is, we know this is an 1 by R cube prefactor, which we have just learned, and it is written as this L dot S term. So the spin couples with two magnetic field. One is coming from outside, which is a B external, another is coming from the inside, which is a relativistic effect on the spin orbit coupling, which is coming because of the which is coming because of the fact that from the point of view of the electron, the positively charged proton electric field is in a moving frame, and that produces an effective internal magnetic field. So from here we can proceed by writing the classic vector potential in terms of this A B cross R, which is a form we can take for uniform magnetic field, and when you plug that in, you get this form. So you have H, so you want to get rid of, separate this this magnetic field term, so it becomes a simple H naught, which comes from the hydrogen atom problem, or for Z equal to 1. Then you have the LS coupling term, which we already discussed about. LS coupling term, which we already discussed about, and we have a term which is L plus 2S dot B, which is basically coming from one part is coming from this external magnetic field being written like this, and another part is coming from this S term, and then we have a B cross R extra term. So just do this algebra, this 1 or 2 lines of algebra. When you plug that in, you get this form of the Hamiltonian. And now you choose for convenience your B external to be along the Z axis with a uniform magnitude B naught. So here is a quick side note to show how to do that calculation at the last line, which I said that you can work it out on your own. So notice that if you have a term P and dot A acting on psi, you can write it in this form, and then you can rearrange it by writing that del acting on this whole, that P acting on this whole of A and psi. So it will first act on A and then it will act on psi, and then you can choose this Coulomb gauge, which is often a convenient choice for systems with cylindrical symmetry. And this under this choice, this Coulomb gauge, this thing becomes 0, and the P dot A can now be replaced by P dot A becomes like A dot P. So when you do that, you write this, expand this square, you have this P dot A and A dot P type of term, and A dot P is nothing but this this object, which is nothing but B dot L. So when you put all this thing together, you will get this term, which is B external dot L plus this, and on top of that, at the end you are adding the LS coupling also, like here. So it's a very easy check. I am not going to much further details of how to do that. So how to work out this form of the Hamiltonian in the presence of a external uniform magnetic field. So now we want to deal each of this term and see how can we understand the effect of an external magnetic field. So let me call this first kinetic term HA, the Coulomb term HB, the LS coupling term HC, the term which is coming from the external magnetic field, which couples with the L and S in this form, which is HD, and then there is another additional term which is order of the magnetic field square. Plus, if you want to do fine structure, you can also add this, to be fair of keeping all the alpha square term, you can also add this HF and HG. But these terms are relatively easier to deal with because they do not contain an spin explicitly, but here we will discuss mainly with the spin type of term, which, because that term will leave the degeneracy and will do some, it will interact in a special way, we will see how. So now depending on the relative strength of the term A to E, it depends on the, which depends on only two things. One is the state of the Pater wave function and the magnetic external magnetic field. So depending on the relative state, we can decide that which part of the Hamiltonian we can safely call H naught and which part as H1, and how can we apply the perturbation theory formalism. So we just understood that there are these two type of term. One is an internal magnetic field, another is an external magnetic field. The internal magnetic field, as we discussed before, it comes from the fact that the electron sees the proton is the source of electric charge, which is in a moving frame, and that produces an effective magnetic field by relativistic effect. And then the external magnetic field is simply the magnetic field you applied. So depending on which part is stronger than the other, you can use effectively the perturbation theory. So here is a bit of number estimate. So the internal magnetic field we calculated to be this, which you can plug in the numbers and estimate that for the smallest possible orbit, L is h bar, R is the Bohr radius, and if you compute that, you will get 12 Tesla. Now 12 Tesla is a very large magnetic field actually, I mean quite large magnetic field, because a typical Earth's magnetic field, for example, is 30 micro Tesla, and typically in a lab it's rarely you will get, like in India there are very few labs where you can get 12 Tesla, and getting a static 12 Tesla field is very rare. So if your B external is greater than 12 Tesla, then only you will have the strong field effects, or the perturbation, you cannot treat it external as perturbation anymore. In that case you have to treat the internal as a perturbation and external as the part of H naught, and this is an order of estimate that how big these numbers are. And actually in a, so just a moment. So now as we established or discussed that in any typical lab equipment, a 12 Tesla is fairly big. So this external magnetic field can possibly be treated as a perturbation, but in present days actually 12 Tesla is easily achieved, and there are even 80 Tesla magnets, but they are not static field, they are of a pulsed field. So to treat that properly, we need to use time dependent perturbation theory. In static field actually 14 to 16 Tesla is fairly big amount, and we will see how we can treat these different effects using this perturbation theory. Now as you can imagine, if your B external is much greater than the B internal or 12 Tesla, you can apply the perturbation theory by treating the B internal as perturbation and B external as the H naught, and vice versa. If it is much smaller than 12 Tesla, like typically in early experiments of this, it was like 1 Tesla magnetic field was used. That was like state of the art in around this late 1897. So in that case it was clearly a perturbative effect where B external has to be treated as perturbative. But it turns out when internal and external are comparable, then you cannot use a perturbation theory between these two anymore, and then you have to take the whole thing itself as an H1, where the H naught remains the other unperturbed Hamiltonian, okay, which is Z square by the kinetic term and Z square by R. So that is an order of estimate that in which part, what kind of situation you can treat this problem as a perturbative problem. Okay. Now strong field Zeeman effect is basically when B external is greater than B internal, and let us see how to treat this. So for the time being, let us neglect the HC and HE terms, and the HE term is basically the Darwin term which gives a diamagnetic effect even for a small moderate strength of B external. And in this case, now the energy when B external is much greater than, the energy due to magnetic field is much larger compared to the fine structure correction. So if there is a meter of terminology, if it is spin 0 or spin is neglected, it is called normal Zeeman effect, otherwise it is called anomalous Zeeman effect, which is completely a historical terminology. There is nothing anomalous about it, or there is nothing normal or special about it. Okay, so now let us try to treat the simplify this problem and see how perturbation theory works there. So now my H naught is HA plus HB, which is the kinetic and potential term simply of hydrogen atom, and then I have a HD, which I think as this whole thing I treat it as H naught, but in this part I treat it as the perturbation. and Hd is nothing but the mu b by h bar b naught times Lz term plus 2Sz, because I already said that the magnetic field is applied in the z direction. Okay, so now let us see what is the effect of this. Also notice that the Hd commutes with this Hd Lz plus 2Sz commutes with L square Lz S square Sz. So, a good, as I said, one of the art of solving this problem is to find a good basis. So, we should work with this basis in which in the basis of Lz and Sz. So, let us work with, so the full wave function is psi nl ml inner product with S ms, all these quantum numbers, and in this case there is also a way to intuitively think that why j and mj are not the good quantum numbers, because in presence of external field it is like acts like a external torque which works on the j and mj, and they are no longer preserved. So, if you cannot take them as a good quantum number. So, now you have this psi l nl ml r, which is basically I am writing it as r theta phi, which is the radial part and the angular spherical harmonics, and we know that the h naught has the following eigenvalues, because now in this basis this part commutes with that. So, that is very trivially I can found exactly without any approximation that n l m l m s is mu b b 0 m l plus 2 m s, because we know that if the h 1 h naught and h 1 in this case commutes, then you can simply find the eigenvalues. Now, there is a way to interpret this physically. It is to say that if you turn on a very strong magnetic field, then the L and S will decouple, even though you have a like the L and S part will decouple, and it will align, and the L and S will independently align along the magnetic field, as if the L. So normally you couple with the J, and this is what happens when you, because you couple with the J is no longer a good quantum number in fact, but when you do this first order approximation, the effective Hamiltonian you will get, which pretends that as if L and S are like two separate angular momentum, and they are like interacting with the external magnetic field, and simply giving a correction mu b b 0 m l plus 2 m s. So, that is basically the effect of a very strong magnetic field. So, as we can see this from here, because in this two term H A and H B and H D we are treating with, we are not treating the H C, H E and H G yet. Okay. So, now let us write down the energy levels in the presence of this strong external magnetic field. As we established, the basis will be written is n m l m s. It will be simply nothing but the original energies, which is minus 13.6 eV by n square, the Bohr atom energies, plus this correction mu b b 0 m l plus 2 m s. Now, with that we have established that this whole thing is our new, the eigen states or eigen values of the new H naught, on which I will treat the fine structure as a correction, because the fine structure part is smaller and this part is the stronger part. So, now I add these fine structure terms, the spin orbit, the relativistic and the Darwin term, and act in this basis, and we have already seen this calculation, that how to work out these terms, and when you do that you will simply get these terms. But there is a little difference, but earlier we did not work in the basis, earlier we worked in the J basis. This time we cannot work in the J basis, because J is no longer a good quantum number. We are working on this ML MS basis or like LS basis, and in this basis if you write down this term, that L dot S will give you a ML MS type of term, and everything else is just simple and straightforward as before, because as here I show it quickly that how the S dot L will go like. It will have only the SZ and LZ contribution, because the field is in Z direction, and you will get H bar square ML MS. So, that is basically the first energy correction, very simple. So, now we put the we put numbers and simplify this expression further. So, if I calculate, I can rewrite because I want to show that what is it in terms of alpha, because alpha is our perturbative thing, our perturbative parameter, or the small parameter of the theory. So, if I can rewrite this as 2 En square by mc square, this factor I can I can rearrange it such that it can be written in terms of alpha. It becomes alpha square by 10 to the power 4 times 13.6 CV, and similarly this complicated factor can be rearranged to be alpha square 13.6 CV. So now the first order correction will become 13.6 CV by n cube alpha square with this terms, which comes simply from the fine structure, and it is also an order alpha square correction. So the fine structure correction in the presence of magnetic field, it becomes this. Okay. So now we will discuss. So now we understood what happens in the strong field, what are the shifts. Now we will discuss this for the weak field. The weak field is the most common and typical case, which was the first one discovered and first one theoretically explained, because in those days the magnetic field was maximum 1 Tesla. So H naught is now my fine structure, and that is the dominating term, and B external is the weak term. So now the good quantum numbers are N, L, J, M, J, not M, L and M, S, because in the presence of LS coupling, N and S are not separately conserved, because it is my H naught. The H naught is the these are the good quantum numbers for the H naught. So what will be the first order Zeeman correction? The first order Zeeman correction will be the D term, which is the which contains the B external, and in this basis. So once I apply this, I have to find the expectation value of this L plus 2S, and that can be simply done. It is worked out in Griffiths. I am not going to the details, very simple. So it is basically this factor, which is known as Landé G factor, with a J average, which is again, because it's we are in the good quantum number J basis, so you can write it in this form. And now if I choose my B external in the Z direction, so far what we have done in this part, I have not assumed the special form. So earlier I was writing the B external as B naught Z cap, but here I changed the notation a bit and wrote it as B external Z cap. We know in this case that the J is simply, once we choose this, the J is simply MJ H bar. So the EJ, the first correction will be simply the G factor is contains all the complicated J and L prefactor, B external MJ. So that is very simple, and we can plug in the mu B values with all the numbers. It is basically 10 to the minus 5 electron volt per Tesla. So after I add all these effects, for spin for this level n equal to 1, L equal to 0, J equal to half, I get this to be the original energy which is coming from the fine structure, and the perturbation which is coming from weak magnetic field to be mu B, B external. It is plus and minus because spin half, it has like two values, and this will tell me that if the degenerate level of 13.6 eV by alpha square due to the fine structure will split like this in the presence of magnetic field. That is a very simple detectable prediction. So we know for hydrogen atom, the first line, the first spectral line of hydrogen atom will lead to these two lines, and that was exactly what Zeeman found, and this prediction correctly predicts that splitting, and you can even estimate the numbers. If you plug in all the numbers, you know exactly what is the energy level, and you will exactly find the numbers or the spectral lines, and that was exactly what matches very perfectly with Zeeman's experiment. Okay, now let us do one complicated case. Let us go to n equal to 2, and now we have to apply degenerate perturbation theory. So n equal to 2 has L equal to 0, J equal to half, or L equal to 1, J equal to half, or 3 by 2. So there are total 8 states. These states are given by, I wrote them as, it is all following Griffiths and Griffiths notation. I wrote them as 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4 is simply now we write everything in the ML, ML, MS, NL, ML, MS basis, because now we establish that in this case this is the NL, MJ, MJ basis, because we establish that is the right basis to work with in this weak field effect. So this is how this thing will look like: NL, J, MJ, NL, J, MJ, NL, J, MJ, and also on. Now we calculate the Gj using the Landé G factor formula. It becomes 2 by 3 for these two states, and then we can easily compute the E and J for these two states, and that turns out to be this 3.4 electron volt 1 by 5 by 16 alpha square. For these 4 states, it will become Gj equal to 4 by 3. Okay. So now and for that you can also compute the E and J for that. So what will be the energies in the presence? So if these are the 8 states, what will be the energies in the presence of this external magnetic field? we know we have calculated how to do it for EJ1, and it will become all these things. So we can simply just plug in our formula. It will become mu b external minus mu b external and so on. So based on what we found, we can plot them. This is given as an exercise in Griffiths. You can just follow the exercise. If we plot them, we will see that the first level it breaks down to this 1, 2, 3, 4, and the last 4 and the fourth and the second level, which is basically the first one is basically all the levels for which the j is half, and the second one for which the j is 3/2, because now we know j is a good quantum number. So the j levels will split in the presence of this magnetic field. So you will see in the first case this level is splitting into these 4 levels, and second case will fall into this level. And as we increase the b external, so the slope of these lines, the slope of this lines is given by this factor mu b minus mu b, 1/3 mu b minus 1/3 mu b, 2, 2/3 minus 2/3 and 2. So as you increase the magnetic level, so you can think these are the 2p levels. The 2p levels are coming from these factors, which is when the L is equal to 1. So they can meet each other. So there will be some level crossing phenomena, and that's why this thing will break down. And beyond that point, if you make it even further stronger, so this thing is called actually Paschen-Back effect. This was discovered much later, which is nothing but another name of the very strong field Zeeman effect. So now let's see to the situation where these two fields are comparable. So intermediate field. So we imagine that there will be a situation, the B external will be so strong that then you can no longer treat it as a perturbation. So what happens under such a scenario when the B external is so strong that you cannot treat it as a perturbation? So let's look at that scenario. So in that case neither the spin orbit coupling nor the Zeeman term dominates. So they together form the perturbation, which is H1 Hc plus Hd, and H naught is in this case the Bohr Hamiltonian. So how the transition happens? It depends on we'll see that how the transition happens from this weak perturbation of when the magnetic field is tuned from weak to strong and via some intermediate value, when all these terms are equivalent and you can no longer apply any perturbation theory. So actually what you have to do, you have to by hand diagonalize it. Like you have to diagonalize the full problem. You cannot use this series expansion kind of form. So let's see how to do that for n equal to 2, and for n equal to 2 means L equal to 1 or 0. So let's set the L equal to 1, the 2p levels. The 2p levels has these two in terms of j values, two sub levels, which is 2p up and 2p 3/2. And let's work. It's a choice because now we are not doing a perturbation theory, so we can choose a basis by convenience, and that basis we choose Lj Mj. We can also choose L Ml Ms. In that case, like in one case the H1 term will become diagonal and H naught will be non-diagonal. In other case H naught will be diagonal, H1 will be non-diagonal. So we choose the basis where H naught will be diagonal. So that is Lj Mj basis. So in that basis, so using as we will use the Klebs-Gordon coefficient such that we can go from this J Mj to L Ml Ms basis. We will need that because calculation of these terms in the perturbation or the H naught or H1 will become easier in one of those bases. So such that we can switch from one basis to another, because we cannot use two bases for the same problem. We have to use one basis. We need to keep in hand the translation language, and that is this translation language, which is nothing but the Klebs-Gordon coefficient. So in this we refer these states as psi 1, psi 2, psi 3, psi 4, psi 5, psi 6, psi 7, psi 8, and on the left side we write the JMJ basis form, and the right side we write the LMLS basis form, and by Klebs-Gordon coefficient, that is the relation. So now let's look at the fine structure term. So if I compute this, the fine structure part, and plug it, sandwich it between these two states, I will get simply this form EFS E2 square by 2 mc square 3 minus 8 j plus half. Now we know that the E2 square and US1 can be related, and I can simply replace this formula and write it in this form. So see, as in this form again I plug in the numbers, and as the Griffiths notation I write it as gamma 3 minus 8 j plus half. Now, because this is how the Fs term looks better when you write it in the J basis. So, J for J equal to half, these are the 4 terms which states which is J equal to half. The H1 Fs will have this term which is minus 5 gamma, and J equal to 3 by 2 it will have this form minus gamma. Now, in that basis we have chosen to work on. In this basis, this Hamiltonian is diagonal, and this is the form of the fine structure form. Now, we will find what is the form of the external magnetic field term. So, in that basis, psi 1, psi 2, psi 3, psi 4 are eigenstates of Lz and Sz also, and that we can see very simply by looking at what psi 1, psi 2, psi 1, psi 2, psi 3, psi 5. So, this is psi 1, psi 2, psi 3 and psi 5, and they are simply eigenstates of Lz and Sz. So, they are diagonal. So, if I plug that in, I will get these forms, which is Hj1 Eh bar by 2m B external ml plus 2 ms times beta, where beta is something, I assume this part, I just write this part whole thing as beta. So, Hz11 matrix element, 22 matrix element, we can calculate each of these matrix elements. They are simply diagonal, they are beta minus beta, 2 beta minus 2 beta, and these ones are off diagonal because of this because in this basis, because it is very easy to see, because you can see that these are the ones which are completely, it does not have any LML type of mixing, because you remember we are writing everything in this basis, we are writing everything LJ MJ basis. In that basis, when I write that but I am calculating the spin or the external magnetic field, it is easy to calculate in this basis, and this basis there is some mixing. So, these 4 terms will have some mixing and they will be not diagonal, and they are the eigens. So, that is why these 4 are diagonal and these 4 are not diagonal, and this off diagonal form can be computed very simply. So, here I have computed, I have written down how will they look like if I calculate this all the terms, the diagonal terms, and then the off diagonal terms also, how will they look like. So, I will suggest you to work out this example once by hand, because I have done it in a very shortcut notation, and that might not be very easy to follow unless you do it in your own hand. So, now I write down the whole matrix. So, if I write down the whole matrix with the Hz1 Fs1 in that basis, and in the basis of our choice, which is LMJJ, LJMJ, and it will look like this. The first 4 terms will have completely diagonal block. The second terms will have, the second psi 5 to psi 8 will have this off diagonal block. Will have some off diagonal contribution, but that can be even also written in this block form. So, now what we have to do, this part is already diagonalized, we do not have to do anything, we have to diagonalize just these 2 parts. So, let us do that. So, if you write down, if you diagonalize this first block, it will look like this. This is the quadratic formula you will get, because now we have to apply this secular equation form. So, you will get this, and the eigenvalues are these, and the second block will be the same exact thing, except the beta is replaced by minus beta. So, now we will get these energies, which is E1, E2, E3, E4, E5, E6, E7, E8, the diagonal energies, and that is the level splitting because of the external magnetic field. So, if I plot it, this is how it will look like, and you will see that as I go from weak to intermediate to strong. So, now everything is exact here. Here I do not care about perturbation, it is done exactly. Sorry, I should not use the word secular equation here. I will just say this is the exact Hamiltonian which I want to diagonalize. So, there is nothing secular or anything, any secular form or anything to be concerned, anything to bother about. Okay. So, if I do the full problem now, then this is my thing, and this is where the levels will cross each other. So, at very weak field, we have already discussed the weak field Zeeman effect. At very strong field, we have discussed the strong field Zeeman effect, and the intermediate field we cannot do anything, and then we have to solve this whole problem by hand. So, that is basically the whole thing about Zeeman effect, and that is where I end this section.